Make sure this works. Okay, thanks so much for having me here. It's always such a pleasure to come. This really is a special workshop, as we heard several times over the last couple of days. All right, so I want to talk to you a little bit about galaxy growth and the cosmic web. We'd heard a lot about the cosmic web today, and we had a glimpse of how the cosmic web affects galaxies. The cosmic web obviously is many orders of magnitude in size from the individual galaxies, and so hopefully we'll be able to elucidate kind of the how individual galaxies are affected by the cosmic web. So first, I want to introduce again the morphology quiescence relation. So we heard a little bit about it yesterday, I believe, that quiescence correlates, we've heard for many decades actually, that quiescence correlates with morphology. And all measures of morphology, bulge mass, velocity dispersion, and so forth. Today I'm going to focus on this core density here, which is the stellar mass density within the inner kiloparsec, or 2 kiloparsecs, depending on the resolution of what I'm using. This relationship where the quenched galaxies, which are plotted in red up here, have higher core density at the same stellar mass than the star-forming galaxies, which are plotted in blue here. This relation has been seen not exactly in these quantities, but it's persistent out to redshift 6, as we heard from Mark the other day. And so one thing that we need to do is that in order to understand quenching, we need to first understand how galaxies grow, okay, particularly how their central densities grow. And that will give us a clue to quenching. So one major clue that we have is if we look at the same diagram of the core density versus stellar mass and color code it just for the star-forming galaxies in manga, and we color code the points by their SSFR gradient, such that blue here means they're forming stars and they're centered, they're blue-centered, and the red points here are the red-centered galaxies, meaning the star formation is happening in the outsides. And we see that galaxies with high core densities tend to have blue centers. Okay, so that's one major clue. They have centrally concentrated star formation, and they've got high core density. Okay. So we tried to understand this effect in the illustrious TNG simulation. This was work done by my collaborator Dan Walters over a couple of papers. And the goal was to understand how galaxies evolve in this diagram here. What determines whether or not their core grows quickly? What determines whether or not their core is dense or not? Okay, so here's the same plot again from manga. And first of all, we checked whether or not we see the same thing in illustrious TNG. And here is the same plot, except now we're plotting the 2 kiloparsec scale on the y-axis instead of 1 kiloparsec because of the resolution of the simulation, and color-coded again by the gradient in SSFR. And as you can see, illustrious TNG shows the same thing, where the galaxies with high core densities tend to have bluer centers. They tend to have centers that have star formation in their centers rather than their outsides. Whereas if you have a lower core density, you tend to have star formation in your outsides. So this is good news. TNG does reproduce this. It doesn't reproduce everything in the visible universe, as we know, but at least this, it does reproduce. So we can ask the question, why? Why do galaxies have blue centers, and why do they have high densities, high core densities? So we looked at the evolutionary tracks of individual galaxies in this diagram while they're star forming. So I just want to emphasize that these are star forming galaxies and they're isolated. So we're not talking about satellites yet. So what we had found was that galaxies that are in the upper region of the diagram, still only star forming, they tend to evolve on steeper slopes in this diagram. So in other words, they build their core densities faster than their stellar mass, than their total stellar mass. So steeper slopes means they're building their core density relatively quickly relative to their whole galaxy. Shallower slopes means they're building their mass on the outsides rather than their insides. So this is how it seems that galaxies that have low core densities evolve on shallower slopes. So that makes sense. They evolve on shallower slopes because they're not building their core densities, and they have less dense cores. Okay, so what then determines whether or not you have a steep trajectory in this plot or a shallow trajectory? By the way, I like to show this plot. This is. I don't know if Sandy you're going to show it this week, but Sandy did show it last year, and it was a wonderful plot showing the evolutionary tracks of galaxies in this diagram, but from manga, assuming constant star formation rates in the centers and on the outsides. And if you do that, then these are the evolutionary tracks, and she finds the same thing, which is wonderful. So it's the same as in TNG. Okay, so what determines the slope of the trajectory in this plot? So what we had found, we tested several different things, but one of the main things we had found was that if you put the slope of the arrow on the y-axis, such that in the lower part of the diagram you have slower core growth, and in the upper part of the diagram you have fast core growth, and the x-axis is the specific angular momentum of the accreted gas at half R-veer, so quite far from the galaxy. What we had found was that if you are accreting gas with high specific angular momentum, you tend to grow your cores slower. So in other words, the slope of the evolution is shallower. Okay? But if you had lower specific angular momentum accreting at half R-veer into your halo, then you tend to have faster core growth. Okay, so that was one major result from this paper, was that the gas angular momentum predicts core growth for at least the last 5 gigayears. Okay, so the angular momentum determines the slope. The angular momentum of your accreting gas determines the slope of your trajectory on this plot. Other things that we had found related to quenching, which was very interesting, was that we had measured the quenching timescale as a timescale between crossing certain thresholds in SSFR, and we found that that galaxies that are more massive take longer to quench. And how is this related to angular momentum? If you had higher angular momentum accreting gas at half R-veer, you tended to quench more slowly. And is this confirmed in observations? The way that we decided we can't do quenching timescales in observations, at least not accurately enough. So we realized that if we want to compare to observations, we could use the age gradient. So if galaxies, the idea is that if galaxies are quenching inside out, which most galaxies are, right? We expect that if you're quenching slowly, and you're quenching inside out slowly, then you should have older centers and younger outsides. So you should have, steeper age gradients. Whereas if you're quenching quickly inside out, then your whole age gradient should be flatter. So first of all, we wanted to confirm this is exactly what we see in TNG. So this is the quenching timescale on the y-axis and the age gradient on the x-axis. And you can see that if you quench quickly, you tend to have steeper gradients, age gradients, lower gradients. And if you're quenching slowly, then you tend to have steeper age gradients. So we can compare it. We can do age gradients in manga. So this is, first of all, the age gradients in TNG, where we have your sigma to the core density versus stellar mass. And now we're color-coded by the age gradient, where greener, bluer means kind of flatter or younger-ish age gradients. Where red means that you're older in the centers. Okay, so this is TNG. What does it look like in manga? Here it is. So in manga, we also have the age gradients such that if you're lower in sigma 1 or sigma 2 and higher in mass, if you're more massive, you tend to have steeper age gradients, so you probably quenched more slowly. Whereas if you have higher sigma 1 or lower mass, you tend to quench more quickly. So this was another major result from this paper. These are all isolated galaxies. We'll get to the environment. I know this is an environment session. We'll get to that in a minute. Okay, so we connected mass, sigma 1 or sigma 2, and gas angular momentum. So remember that we had that the angular momentum is lower in the upper part of the diagram and higher in the lower part of the diagram. So the gas is accreting onto the outsides if you're lower in the diagram. Okay, so here, what we had determined then, this is just a cartoon of what we had discovered, was that if you're accreting gas with low angular momentum, then you'll evolve more steeply in this diagram. If you're accreting with high angular momentum, you'll evolve more shallowly in this diagram. And it turns out that you quench quickly if you're on this track, and you quench slowly if you're on that track. So that's a summary of that particular result. Okay, so why is it then? So we discovered that angular momentum is connected with the evolution of the central density of the galaxy. So why is it then that you accrete gas with high angular momentum or low angular momentum? What causes that? And so the idea that we had, my collaborators and I, including Joel, Sandy, Farhan, Doug, and this illustrious student right here, my student undergrad, Marcus Cowan, did all the work that I'm about to show you. But basically, the idea was that the position in the cosmic web determines the angular momentum of the accreting gas. So that was the idea. So the idea is that if you're in every galaxy, as we heard from Farhan today, every galaxy is in at least a little filament. Some of them are in big filaments. But every galaxy is in a filament. And if you're in, the idea is that if you're in a thinner filament, you'll be accreting gas at a different angular momentum than if you're in a thicker filament. So here it is in cartoon form. Okay, so if you're in a thick filament, you could be anywhere along it. A gas is probably going to be going along the filament, but you could be accreting with low angular momentum or high angular momentum. Your probabilities of low angular momentum are a little bit lower. But if you're in a thin filament, then you're more likely to be accreting gas with low angular momentum. So you're more likely to have your gas fall into the center of the galaxy. Okay? So that was kind of the idea. Joel likes to call this picture a bead on a string. So these galaxies are kind of like a bead on a string. The dark matter halos, yes, are like a bead on a string. So this applies, by the way, for filaments. This is my cartoon version of a node. So if you have not just for filaments, but nodes, of course, are higher density environments, and this applies in the same way. But galaxies in lower density environments will be in single filaments like this. Okay, so let's take a look then at the same diagram. So this was the core density versus stellar mass, and color-coded by the gradient in SSFR. So remember, higher core densities gives you bluer centers. So we also had this diagram color-coded by the specific gas angular momentum accreted at half our Vir, so quite far from the galaxy. And what we see here is that, indeed, if you have high sigma 1 compared to your mass, or high sigma 2, high core densities, you are accreting gas at lower specific angular momentum. So your gas is actually accreting onto your, or more likely to be accreted nearer to your centers of the galaxies. So this is, first of all, the galaxy. Now, what about the filaments? This is a preliminary result. By the way, this is the specific angular momentum of the gas accreted at half our Vir on the y-axis. And the x-axis here is the local dark matter density averaged over 1 megaparsec, but this is very similar at different scales that we're averaging the local dark matter density. So this is a measure of your filament environment. So if you have thin filaments, you're going to be at lower density. If you're in a thick filament or node, you're going to be living in a higher density environment. This x-axis, by the way, was computed by Doug Hellinger here in this room. And we also plotted the same thing against distance from the filament computed by Farhan, and we see similar results. Although and here we have the different curves in different mass bins as well. So as you can see here, if you are in a higher density environment or a thicker filament, you tend to be accreting your gas with higher specific angular momentum at half our Vir. All right. So, and if you are in a lower density environment, the angular momentum of your accreting gas is lower. So this picture so far is, by the way, we're still looking at star-forming central galaxies. And so this picture of being in a thinner filament means you're more likely to be accreting with low angular momentum seems to be supported by this picture. And not only that, here we have, this is another result from Marcus. Here on the y-axis, I'm showing the distance from the best fit line of the core density versus M star plot. So the distance, the little arrow, the distance from the line. Okay? So remember that if you're above the line, you tend to have bluer centers. You tend to be accreting at lower angular momentum. And if you're above the line, you're higher up in the y-axis. And if you're higher up, you also tend to be in lower density environments or thinner filaments. Okay, so all, again, divided by stellar mass. So the picture of, so why is it? So this is one clue. Perhaps we heard earlier yesterday from Corentin, great talk, that the angular momentum of the accreting gas in your halo tends to get mixed up by the time it gets to the bottom, and we're seeing that even though the core densities tend to be correlated with the dark matter densities, the actual color gradients are much more weakly correlated, which is very interesting. So on a shorter time scale, which measures the color gradients and the SSFR gradients, the relations tend to be a lot weaker. But on longer time scales, which measures the build-up, the slower build-up of the inner density, we are seeing this correlation between filaments, the dark matter density, and the angular momentum of accretion, and the build-up of the galaxy core. All right, so in summary, then, the central densities of galaxies are an important indicator of their past and future evolution. In particular, star-forming galaxies with high central densities tend to have younger or bluer centers than galaxies with low central density. Right? So the bluer centers are in the upper part of the diagram, in other words. So while they're star-forming, if you're accreting your gas at low angular momentum, you will tend to evolve steeply in this diagram. So you will tend to build your core more quickly than the outsides, and you also will tend to quench more quickly as well. Whereas if you're accreting your gas on the outsides of your galaxy, you'll tend to evolve in a shallower trajectory on this diagram and quench slowly. And galaxies with high core density tend to accrete gas with lower angular momentum. Okay, so this is a little bit of a corollary of this other result. And finally, low angular momentum accretion is associated with regions of low dark matter density in the cosmic web. Thank you.
Before time, so we have lots of time for questions. Maybe I should go from the back.
So this was a great talk. So my question is that when you're looking at these correlations between environment and galaxy properties, there's a tertiary correlating variable, which is the accretion rate of the halos. So that also depends on environment, and galaxy properties also tend to depend on that. And so I was wondering if you've looked into how you separate accretion rate and angular momentum when talking about these sorts of effects.
Yeah, great question. I kept shortening by shortening the x-axis or y-axis by saying angular momentum, but it's actually specific angular momentum. So we have taken out the mass of the accreting gas from these from the y-axis variable here. So the mass accretion rate has been accounted for in that sense.
Thank you very much, Joanna, for the nice work. So one question was that. I have another question is, so I can understand that, you know, low angular momentum leads to faster build-up of the central region, but I didn't get why then you quench faster. if you keep accreting. So at some point you need to stop accreting gas, right? So
Yes.
when this happens and how is this related to, I didn't get that.
Yeah, that's a great question. We were really surprised by this result that more massive galaxies, because if you look on the x-axis, it's more massive galaxies tend to quench slower, which was really surprising. But if you think about it, if you're accreting gas on the outsides of the galaxies, you're looking at the galaxy quenching inside out. And if you're slowly still accreting things on the outside, then the quenching kind of happens on a slower scale. That seems to be that was kind of our thought process a little bit.
There's another way to dump low angular momentum gas into the center, which is like a major merger, gas-rich merger. So I'm wondering, what about that pathway? Are you only talking about star-forming galaxies that don't have major mergers?
Yeah, so we were only looking at isolated galaxies. So in that case, the merger, we made sure that the time since the last major merger was rather long. I don't remember exactly what the time scale was. So we had seen that mergers do affect how steeply you're evolving on this plot. And mergers do steepen the relationship, as you would expect. But it's because the mergers are so few in this sample, because we selected them to be isolated, it's not a huge contributor.
So maybe it's a dumb question. I was wondering, isn't the low specific angular momentum a manifestation of their compact sizes rather than explanation? Right?
So the angular momentum of the gas is measured at half RVR, and they have to be infalling. So it's actually not.
What do you mean by at? So it's everything within RVR?
No, it's at
within
half RVR.
Half RVR.
Yes. So within a little shell at half RVR, measure the angular momentum of the infalling gas.
But are you sure these are the main gas supply?
That's a very good question, and we have seen in lots of people's simulations, including the talk we saw yesterday, that it doesn't necessarily have to end up right at the center of the galaxy. And so actually what we had seen was that if you are accreting, let's say if your angular momentum of the accreting gas at half RVR is high, then for sure all the correlations are quite a bit stronger. You don't grow your core density. Your core density, the relationship between your SSFR gradient with angular momentum is stronger when you have higher angular momentum. But at low angular momentum, you are not guaranteed. So basically, if you have high angular momentum, you're guaranteed to be accreting on the outsides. But if you have low angular momentum, you're not guaranteed to be accreting on the insides. So there is quite a lot of scatter at low angular momentum, and this is preliminary work, and this is work in progress, and we are exploring some of those reasons why. So that's a great point.
Joanna, thanks very much for that great talk. I think the Simon Fraser students are very lucky. So, very naive question. How did you decide to use half RVR instead of something much smaller, like a third or a fifth or something like that?
Yeah, that's a great question. So we did look at different scales, and the angular momentum at half RVR is correlated going down to lower scales. We had tried to pick a radius with a round number that was away from the galaxy. We wanted to understand and see if the accreting gas has some effect on the galaxy, particularly the core formation of these galaxies, or the core buildup of these galaxies.
Great, thanks.
I'd like to return to that question of the rapidity of quenching.
Yes.
Okay, so simple question. Did you decide that there was a difference in rate having looked at the simulation and seen that it was true? Or did you think in advance from first principles that it must go that way?
So we did not think in advance. We looked at it. I was expecting from first principles and from others to high redshift studies that the more massive galaxies should be quenching first, or faster, right? They're quenching the top down, or the, what do you call it? The downsizing is the term, right? The downsizing idea where the most massive galaxies are quenching earliest and so therefore fastest, right? But when you think about it, the high redshift studies they only look at galaxies that have already quenched by then. So they've completely missed ones that are currently still quenching and therefore have longer timescales. So we looked at the simulation and we saw that more massive galaxies take longer to quench. But then we decided, okay, well, let's see if this is true in observations as well by using the age gradient as a proxy for quenching timescale under a whole bunch of assumptions. And we saw that it was also true in observations. And the explanation as to why is a little bit harder, but I think it has to do with the accretion on the outsides being kind of a trickle and allowing for longer star formation over longer times.
There was an interesting juxtaposition of your talk with Xiaohan Wang's talk just before it.
Yes, I forgot to mention.
So an interesting question is the connection and correlation between these two different kinds of star-forming galaxies, the ones that they call the pseudobulges, which just means low central density, and the ones that they're calling elbow, which means star-forming but high central density.
Yes.
And to what extent is it that is more or less the same as your two different kinds of galaxies, the red center galaxies and the bluer center galaxies, the high central density?
So
but
yes.
let me ask.
Okay.
At the very end of her talk, Xiaohan raised the question: where do those galaxies come from? Could they have come from the pseudobulges evolving into the elbow bulges, let's call them? And my guess is that you would say, oh, no, that's not the way it works at all. The ones with high central density will stay high central density and quench that way and become Green Valley galaxies fairly quickly. And they didn't come from lower central density galaxies. In fact, this is an idea that Sandy's been pushing for some time, that the relative amount of central density to stellar mass stays the same. Sandy calls that a track. The ones with the high central density would be high track, and you would not expect to see low track galaxies turn into high track galaxies if that is something that's preserved.
Except that we do see, and Sandy sees as well, that the tracks aren't just parallel to each other; they diverge, right? So the steeper tracks do come from lower down, so they do evolve in their core density. So I do think that it is totally possible that the pseudobulges evolved to classical bulges.
The question that was raised was,
Some.
Can you change the radius that much?
Yes, that's something.
Central star formation will decrease the relative radius, but not all of that, not by half a jet.
Yes, you're right. So I don't think as much as I should on the radii, which Sandy thinks a lot about, because I've been thinking a lot about the central density. But that's a great question and a good point. Yeah.
Let's thank the speaker again, and let's populate the Google Doc if you have questions.